homework floating about?
Yes.
Yes, any questions on that homework?
Uh,
I think it's the Laurent series one, or?
Yeah.
I think I
Yeah.
got somebody's, I got
I gave
yours.
mine.
Okay, cool. Thank you.
wow, always on time with your stuff.
I was early this time.
Wow.
Super early.
It was technically due today.
I was gonna have it done today, and then COVID.
It's okay. Is that, the start of a question?
Maybe I had a series where it was a power series, but only in terms of this even terms. The other
Okay.
ones were zero. And so,
Yeah, I know which one you're talking about, that sounds right.
yeah, I did a thing to make that not so bad, but I was wondering if you could show what you're supposed to do to show that like converges.
You don't have to, so the convergence will come, which one was it, Noah?
It was, I think it was just one.
Can you tell me what the actual function was?
Sine of z minus sine of z over z to the fifth.
Oh, okay, so do not, over z, what was it?
To the fifth.
To the
Well, I've already done the problem, so anything you're telling me to do not do might be too late.
So I wouldn't go through, I wouldn't generalize this series and write it in, with an index and then use some sort of test, like the ratio test probably, to find the radius of convergence. I would use the fact that we know there's a definite singularity at zero, right? And we're expanding at zero, but there's no bounds out this way as to stop. Sorry, let me start this again. So this thing here, this is defined everywhere.
Yes.
This has an infinite radius of convergence. So does sine. And then we divide by the z to the fifth. And really the effect that this has is takes out zero. So our radius of convergence will still be infinite because there's only one singularity at zero and we're expanding at zero. So you could just use the fact that everything else here has an infinite radius of convergence and argue it that way.
Okay, I'll do that in a few.
Yeah, it's so much easier. Yeah, that would be painful because I don't think it's a very chill. It's not too bad.
It's not too bad, but if you were to do, like, the problem is if you did the one that was a over a n plus 1 over a n, one of them is always a rational number and one of them is always zero. So it keeps switching between 0 and infinity.
Oh,
So the limit does not exist and
Right.
you have to do a different test.
yes.
Or you could do a different thing and just be like,
So generally, actually, probably, do you remember this? Did you?
the limbs.
I don't remember if you had
Yeah,
analysis with me or.
I did.
Yeah,
I vaguely remember something.
but this would be a better formula if we knew some analysis. Take the limit superior. So the limit superior will be that positive value and the zero won't impact it
Okay.
at all. Does that make sense?
Yeah.
Yeah. Well, yeah, no, maybe not. I just, for these, when you're working with known Taylor series, just use their known expansions.
Okay.
And radii. Any other questions on that problem set? Okay, cool. So we have 3 classes today and then 2 more, which is so sad. And on Monday, I will give you your take-home final and talk a little bit more about some stuff. I want to do some applications toward real integrals, but we got one more thing we need to talk about. And some of this is definitions, so I'm going to be a little bit speedy as we go through it. But let's say I've got a function and I've done a Laurent expansion for it around Z naught. So we're gonna do a Laurent series at Z equals Z naught, and that's gonna look like this, dot, 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 plus. I'm gonna have a to the negative 2 over Z minus Z naught squared, a to the negative first. What's that coefficient called?
The residue?
It's called the residue, yeah. That's what today's gonna be a lot about. And then we have the constant term, and then we move into the more traditional looking piece. Here, the positive powers. This is called the analytic part. And this is called the principal part. So the first thing we want to do is just get a little bit of terminology for the different varieties of things that can happen here. So first off, let's just say that the principal part is all 0. So let's just look at a few cases here, and let me find a better pen. That's good. So the cases, a negative 1 equals a negative 2 equals, that's all 0. So this piece is gone, and I've just got a normal old Taylor series. If that's the case, then F has a 0 of multiplicity M. And M is a positive integer. If F of Z can be written as Z minus Z naught to the mth power, so I can factor out something that looks like this, and it has a power of M on it, and then this G of Z, that's not 0 at Z naught, so all the 0-ness comes out right here. So where G of Z naught is not equal to 0. Let me give you a couple examples here. Let's see here. Okay, yeah. So right here, kind of an interesting example. I've got e to the z cubed minus 1 over z. Now 0 is a problem here, and I'll get to the problem that is. But let's just do the Taylor series for this, and see what the series expansion would look like at 0. So series expansion at z equals 0. So first I would just go to what I know about E, and E looks like this. This is something that as a mathematician you want to be able to just produce instantly. And if you can't, I would have this on my sheet for sure, just for reference whenever I'm working with series, and then eventually you'll just know it. So I'm going to replace this box with z cubed and simplify. So this is going to equal, let's put the 1 over z out in front. I'm going to have 1 plus z cubed plus z cubed squared is z to the 6th. And then that's over 2 factorial plus z to the 9th over 3 factorial plus blah, blah, blah. And then that's going to go on. I'm going to put that in parentheses so I kind of group it together, but I subtract off 1. So 1 cancels with the 1. I set that up so that it would. And this is equal to 1 over z times z cubed plus z to the 6th over 2 factorial plus z to the 9th over 3 factorial, blah, blah, blah. And now let's cancel the z out. And what we've got here is z squared plus z2, is that right? Yes.
Yes.
Yes, z to the 5th over 2 factorial plus z to the 8th over 3 factorial, blah, blah, blah. Now let me stop. Does that make sense? Do you see how I'm getting that? So notice what we've got here. I can pull a z squared out of each one of these terms. So I can rewrite this as z squared times 1 plus z cubed over 2 factorial plus z to the 6th over 3 factorial on down the way. So it looks like 0 is, z equals 0 is a 0 of multiplicity 2. So this is the z minus 0 squared thing out in front here. And then this piece, when I plug 0 in, is 1. So this is the g of z part here. Notice that g of 0 is equal to 1. So we're good to go. So 0 is a 0 of multiplicity 2. Not obvious at all when you see this thing right here. Noah, what is the radius of convergence?
You know, I'm just gonna say what you said and say infinite.
So it's everything, right? So infinite, except for 0. So the disk of convergence here would be everything except 0, because we can't let z equal 0. Even though this turns out to not be a true singularity at all. It's just a fake looking one. It looks like trouble, but it ends up not being trouble.
But what if, like, you have an a to the 0 there?
Say that again?
If you have an a0, can you still factor stuff out or no?
If you have an a0, can you
So if you have a non-z part.
give me an example, because I don't think I understand.
Just like the same thing but without the -1.
Oh, with that, that would be trouble. Yeah, absolutely. So let's take a look at that. Gotcha. So if I had e to the z cubed over z, this
Yeah.
is what we're thinking. That's this trouble, because what I've got is the series for e to the z cubed, which is 1 plus z cubed plus z to the 6th over 2, blah, blah, blah. But then when I divide, you're right, I do have trouble there. So that is 0 here is a singularity. A very certain, a very particular type. But does that help?
Yeah. I think so.
Okay. We're going to talk about, this is where I'm moving, so it's actually a pretty nice segue. So thank you. Thank you for that.
Anytime.
So when there's no principal part, we can talk about zeros. When there is a principal part, we've got a couple of this thing, son of a gun. This chump.
Bad eraser.
Oh, it's terrible. Bad board, bad eraser.
Let's do the school.
I think our damages might be a little limited. It could be a small cap on them.
Yeah, but like, you gotta go for anything you can get. You know.
This is true. Well, I'll sign on to it after you write it up.
Yeah. My brother will be a paralegal soon or something. I don't know.
Well, my wife's a lawyer, so she can tell us that our suit has no chance of success. Okay, so let's look here. So, if a to the -1 is not 0, but the rest are, so there's only this piece here, just like over there, but a2 is equal to a -3. Those are all equal to 0. As I said, just right over here with this example, here I have a to the -1 is 1. Then we have a simple pole at z equals z naught. Then f has a simple pole, P-O-L-E, at z equals z naught. So we call these blow-ups, these places where we're dividing by 0, poles. And a simple pole is this one here, where nothing else exists. If a sub minus m is not equal to 0, but everything to its left is equal to 0, so a minus m plus 1, here, let's do it like this. A minus m minus 1 equals a minus m minus 2 equals 0. So the last non-zero coefficient is the 1 over z minus z naught to the m. So keep that in mind. Here's the term that goes with. Matches with that. If that's my last negative power term, I have a pole of order m. F has a pole of order m. So it's kind of like the 0 that we were talking about, a 0 of multiplicity m, but it's a division by something that goes m levels deep with its zeroness. So it has a pole of order m at z equals z naught. Cool. So let's take a few examples here. Maybe get some tools out. Do I have any good examples? Yeah. Looks like I got on page 292. I have a mark to myself. Note to self. Page 292. Let's take a look at number 7 and number 8. So number 7, let me get that up here. We're gonna practice some of this stuff up. In the first couple, we're gonna do super low hanging fruit for this first one. What is the order of the 0 or poles? So if I have f of z at z to the 4th plus z squared, what do we got here? Do we have poles? Do we have 0? Because that's a Laurent series, centered at 0. What do we have? Do we have any negative coefficients? No. So we don't have any poles. What do we have?
0 or 2.
Yeah.
So just check this out. I just pull out the highest power of z that I can, and I'm good to go.
Okay. So what if that series had a +1?
Then I would not have a 0 of order 2 at 0, but I would have other zeros.
So could you do the thing where you pulled out a thing?
Yeah, let's take a look. I like your question. So right now, notice that this part is not equal to 0 at z equals 0, but this is. What I'm saying is this piece here is not 0. Get a little confusing. So notice, well, what happens if I have 1 plus z squared plus z to the 4th? 0 is no longer a 0. But I have other zeros, and I would have to get out the quadratic formula now. So this would be -1 plus or minus something like this, and then that's going to be -1/2 plus or minus square root of 3/2 I. And then I have to take the square roots of each of these things
Yeah.
to find the z. And what's going to turn out, Noah, is that I've got 4 different zeros, each of order 1. So I will end up, the square root of this, or the 2 square roots are going to be 2 different numbers. And then the 2 square roots of this will be 2 other different numbers. And each one of those will only occur once as a 0. Does that help? Does that make sense? You're pondering.
I guess
see.
so you can have a thing of multiplicity 0 then. Because like you can't pull out, even though that is centered at z0, you can't pull out a z of 0.
That's right. So I guess we just wouldn't say it had a 0 at all there.
Okay,
Yeah,
cool.
yeah.
Great.
Good stuff. Let's take a look at number 8. So number 8, I'm gonna ask you to do this one. Man, I'm smelling food. It's crazy. All right, so number 8 is, well, let's actually do number 9, now that I look at it. We have e to the 2z minus e to the z. What kind of 0, at 0. The 0 will be at 0 if there is one. And in fact, how do I know there is a 0 at z equals 0?
We can plug in.
You can plug it in to see that the function's 0 there, right? So if this is f of z, then we know that f of 0 is 1 minus 1 equals 0. So there is a 0 there. How deep does it go? That is what we have to figure out. And to do that, get to the series. Look at the series. I'm going to give you another test in just a minute, but I want us to practice with the series. Just naively writing down the series, and I'm just going to combine what combines and cancel what cancels and see what's left over. And that lowest coefficient, that's going to be the one, the lowest power coefficient, or term, is all that matters. What's the first z that we see after everything cancels out? Don't need to get too crazy. You don't have to start worrying about combining a lot of things.
Well, what if we did?
Well, then you'd be Noah, probably. So, notice we have, is this cool here how I got these? Good on that? So I got 1 minus 1, 0. 2z minus z, a single z. I don't really need to go any further, but let's just do it. This is 2z squared minus a half z squared. There's probably prettier ways to do that.
I think that should be a plus and not a minus. For the
You are correct, thank you. Yes, absolutely. So I notice I can pull a z out of this, and I'm left with something that does not equal 0. When z equals 0. So here I have a z equals 0 is a 0 of order 1. It's just a simple 0. So you can always go to the series to check your intuition, to get your answers. Sometimes that's a fun and simple way to go. But we also have another result. So z has, f of z has a 0 of order m if we have this derivative condition going on. So let's check this out really quick. Here's a quick proof of this. Proof. And this is an if and only if, in fact. So let's say f of z, our f has a 0 of order m at z equals z naught. I go to the definition. That means f looks like this. And then there's some function g of z here, and g of z naught is definitely not 0. So now I go through and start differentiating, because that's what this theorem's all about. So notice that f of z naught is 0. What's f prime? So f prime of z, I have to use the product rule. So I do the derivative of this part first. That's power rule. Leave that alone. Now leave this first part alone and take the derivative of this piece, which we're assuming exists, apparently. So now, notice that f prime of z naught is still 0, because here, when I put in f prime of z naught, I'm going to get a 0 here, and I'm going to get a 0 here. And if I just keep on doing this until this exponent dies out, I'll find myself at the nth derivative. Now this is going to get very complicated, and I kind of don't want to go that far, but can you see that if I differentiate this thing m times, some version of this piece, this thing in front will go to a constant. In fact, that constant will be m times m minus 1 times m minus 2, blah, 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 m factorial, essentially. And I'll still have that g of z in there. And this piece will be non-zero at that nth derivative. But I'll always have a z minus z naught up until that nth derivative, when this piece dissipates completely. So let's go over here to our last problem. Ooh, let's do a different one. Example. Find the order of the 0, z equals 0, of sine squared of z. Let's say f of z is that. Suspicions on what that order might be? Think about the series. Think about a sine series.
Just 1 or maybe 2.
Definitely 1 or 2. Intuitively, sine looks like this. Let's think about it. Sine looks like this. Minus plus, and we're going to square that. So when you do the first times first, you get a z squared. Your lowest power will be z squared. So I suspect order 2. But let's use this cool and easy method. So first off, notice that f of 0 is sine squared of 0, and that's certainly 0. Now I got to start taking derivatives. So f prime of z, chain rule, and f prime of 0 is equal to 2 sine of 0, and that's going to be 0. Cos of 0, that's 1. Hey, but that's still 0. So I keep doing this until I don't get 0 at the point of interest. And that's going to happen on this next one. F double prime of z, hey, could you find that derivative for me to practice taking derivatives? What's the derivative of that? Take it and see that it's not 0 when you put in 0. Yeah, answer, it's okay, it's all good. Happy to explain any of that. You should get F double prime is 2. And if there's any questions, let me know. Good on this. Cool, cool. So similarly, we have a similar result to this and a similar way of thinking about it, but F has a pole of order M at Z naught, if I can write it like this. So it's very analogous to that product that I have, except here we have a quotient. I've got a G of Z on top and a Z minus Z naught to the M on the bottom. And the top thing does not equal 0 at Z naught. Because if it did, I probably would have canceled this out anyway. If this thing has a 0 at Z naught, I should have canceled out one of those powers and not had a pole of order M. So, how could we detect if we have a pole of order M? Well, the thing we do is the following. Here's the test. F has, this kind of a theorem, I guess, has a pole of order M at Z equals Z naught if, when I multiply F of Z times Z minus Z naught, so I'm going to put that in front, and I multiply that by F, see, I'd be left with that G part, right? If I multiply both sides by this, I'm left with the G part, and that's not 0. Now I want to be careful here about just plugging in 0. So we're going to say the limit as Z goes to Z naught. That's how you plug a value in when you're concerned there might be weird stuff going on. This just means this thing here, if you plug in Z equals Z naught, you get non-zero. So, one last thing here. Let's see, do I have an example I'm going to take a look at? Yeah, let's just leave that there. It will come back to it. Oh, I do want to look at theorem 643, so let me take a look at that. Theorem 643. Here we go. This is a great theorem that we will use to build examples, and you can use to argue as well. So, theorem 643. This is all about a pole of order M. So if G and H are analytic functions at Z equals Z naught, so that means we're not dividing by 0 there. There's no weird stuff going on. There's no blowing up to infinity. There's no holes at Z equals Z naught. And H has a 0 of order M. Order M at z equals z naught. And g of z naught is not 0. So we're learning how to construct examples here. Then, this new function, f of z over, g of z over h of z, this function has a pole of order m at z naught. I'm going to put a nice example to this. So here's how you build all sorts of examples for yourself. Might need to do that for the exam, I'm not sure yet, could happen. I'm going to discover our exam over the break. Try to write a good one. So for example, let's say I have f of z equals cosine of z over z to the fifth. What do I have at z equals 0? A pole, definitely a pole, right? What is the order? 5. Think about what the cosine series looks like. It starts with a 1. 1 minus z squared over 2 factorial plus blah, blah, blah. You're going to get a 1 over z to the fifth in that series. And that's the lowest term you have. So here, because cosine of 0 is not 0, it's 1, and the bottom has a 0 of order 5 at 0, then this function has a pole of order 5. So a really nice, straightforward way to figure this out. Okay, that's about all I wanted to say about zeros and poles. That's all terminology. What we want to do is identify, so I give you a function, we want to be able to look at it and go, okay, there's clearly a pole in it, and the key thing for us is identifying poles. In particular, a very special part of poles, it's that residue that I was talking about. So let's get an official definition up here. If f of z equals, and it's just going to be that same Laurent expansion. That's a sub negative 1, it's a little sloppy. Blah, blah, blah. Oh, I guess one other thing I should mention is if these never end, if the terms never end, you have what's called an essential singularity. So a pole is when this is a finite, kind of like a polynomial is when this part is finite. A pole is when this part is finite. If this part just keeps on cruising, that's called an essential singularity. Regardless of what it is, this coefficient is going to be of utmost importance to us. So we define the residue, of f at z equals z naught by residue, so here I put f of z, and then here I put z naught, whatever the point is just that coefficient over the z minus z naught to the first term. It's just this number right up here. Let's see if we can find the residue from this thing. Right now, we don't have any tools except series. I'm going to give you some better tools, for sure. But let's look at this one here. simplify. So this becomes a z cubed in the bottom. I'm going to put that 1 over 2 factorial on top. And then this one's going to be plus 1 over 4 factorial. Notice that I got z to the 5th in the bottom, z to the 4th on top, and I got a z right there. Doesn't matter what else comes. This is my residue. So I would write this as the residue of cosine of z over z to the 5th at 0 is 1 over 4 factorial, so 1/24. So if you got the series, you're golden. Just look at the series, grab that coefficient, and life is good. What if we don't? So let's get some calculus tools to help us find them. So the step 1 is identify the order of the pole. You kind of need to know how deep is this pole before you extract the residue. So assume we know z equals z, and I'm going to do a couple cases here, is a simple pole. In other words, of f of z, i.e. f of z has some series that starts at this term. This is the most left term. That's what it means to be a simple pole. Then I've got a naught, then I've got a1. Now it starts looking like a polynomial over here. I want this dude right here, and maybe I don't want to crank the whole dang series out. I know that this exists in the eye of the great eye. I could find it, given enough time, but I don't want to. Notice that if I multiply both sides of this equation by z minus z naught, I literally get a to the negative 1 plus a naught z minus z naught plus higher powers of this dude.
But you've just multiplied both sides by 0 if you plug in z naught.
Yes, but I will get something out that's possibly non-zero, that is non-zero. So I'm going to take this limit here, Noah. So let me address what I think is your concern. Yeah, I did multiply by something that's going to go to 0, but think about if I just had this. Here's my series. I've got a pole, a simple pole at 2. If this is my whole series, this is a Laurent series. Oh, here, there, whatever. Here, let's go ahead and add another term on. This has a simple pole at z equals 2. When I multiply by z equals z naught, or excuse me, z minus 2, I get the 1, and then I get this piece here. And then when I take the limit, I actually end up getting a non-zero thing. So the reason I get a non-zero thing, Noah, is because this thing over here, this f of z already is behaving badly at that point. And so I'm just removing that division by 0.
Okay.
Yeah. So this is your formula for your residue. So if you have a simple pole, the residue of f at z naught is this limit z minus z naught, z goes to z naught, z minus z naught times the original function. And this is how you extract. This is called extracting the residue,
Wow.
which is cool.
Yeah.
The terminology is just so beautiful.
Yeah.
Yeah. Even just calling something a residue is cool. I just always loved that word. It seemed so mysterious before I knew anything about complex analysis, and then it just seemed gorgeous. And I'm grateful for it. that's how you do a simple pole.
If you have a pole of order m, would you say multiply it by z minus z naught to the m of both sides?
I like the way you think. It's kind of where I was headed. Let's take a look. It's close to that. We have a little tweak to make. So suppose F has a pole of order m at z naught. Then we know that f of z must look like this. Let's get a couple more. So that's minus m plus 1, z minus z naught minus m plus 1. And eventually we'll make our way up to minus 1 here. Then I'll have constant, nice analytic stuff to the right. And we know that a minus m is not 0. So Noah, you're right, like that's a good suggestion. Noah's suggestion was, what if we multiply, kind of following the same argument, let's multiply through by that denominator there. So what does that look like? So let's multiply both sides by this. And what do I get? What comes out over here?
A minus m. A to the minus m.
A to the minus m. So not the residue, right? Not quite the residue, because then the next one's going to be a to the minus m. What will I have? What's the next term? Somebody tell me. I'll put the coefficients so you don't have to say that. Oh.
Z to z minus z naught.
To the first, yeah. And then I'll just do one more.
Oh no, you're gonna have to take a lot of derivatives.
This is right, yes, so eventually, so check this out, we'll get to a to the minus 1. And notice that this power plus what I'm adding, let's see, wait, so this, I'm trying to find the rhythm of what this power would be here and explain it. This should be,
To the m minus 1, right?
yeah, it should be the n minus 1. Yeah, absolutely. And then the next one, then we have, yeah, exactly, because then the constant term up here would just pick up that. There we go. Yep, cool. Okay, we want this. So if I plug in z equals z naught, all I get is this. That's not what I want. I want this dude. So Noah, I think you said something. What should we do first?
I mean, we could just take m derivatives if we
Yep.
hated ourselves.
It's not too bad. Because we're gonna do it here. It's gonna be horrible notationally. But check this out. If I take the first derivative, what happens? This dies. This is a constant, so it goes to 0. This becomes the new constant. Do you see what I'm saying here? If I take the derivative, this goes to 0. This just becomes this, a constant. This goes down in power by 1. Each of these goes down in power by 1. But what I need to do is take derivatives until this part is completely gone. And then plug in z minus z naught. So what I have to do is take m minus 1 derivatives. So I'm going to say d m minus 1 over d z m minus 1 of z minus z naught f of z is equal to, what will we have? What will I have? This will go to 0 by that derivative level. This will have died. This will have died. What will be left?
A minus 1 to the m minus 1 factorial.
Yep, a minus 1 times, think about every time you do a derivative of this thing. The first time m minus 1 comes out in front, you've already got that. The second time m minus 2 will come out in front. And so eventually what you're going to get is m minus 1 factorial times a minus 1. Yeah, and then the next term will be a naught oh God, what will be there?
A dot, Z minus Z naught.
Yeah, they think like M factorial over,
N minus 1 factorial.
yeah,
No, M
No.
factorial divided by 1 factorial.
yes,
And the
yeah,
next one
M
will be
factorial,
M,
which will look
M
the
plus
same.
1 factorial over 2 factorial.
Yes,
And then yada yada yada.
Exactly.
Yada,
and a Z minus
yada. Z naught.
Z naught.
Yeah.
So when I plug in Z equals Z naught, this stuff will all go to 0. But this will remain. So our final answer is, if you have a pole of order M at Z equals Z naught, then the residue of F at Z naught is the limit. We're gonna just practice this for the rest of the hour. Limit as Z goes to Z naught of Z minus Z naught to the mth power. Derivative, sorry. The M minus first derivative with Z minus Z naught first multiplied in there. So you first multiply by this thing, then you take your derivatives, then you do your limit. So let's practice. This will become our main work for the rest of the semester. We're going to be doing integrals, and what I'd like you to do before our second to last class when we return on Monday is please read read through 6.5. Again, I had recommended that already. But read through 6.5, and then, just read through 6.5 and you'll be golden. Maybe work a couple odds, work some of the odd problems, see if it's making sense to you.
Alright, really quick, what if
Yeah.
we have an essential 0? How do we find the residue of that?
Oh, so if we have an essential 0, we have to go to the series.
That's it?
Yeah, that's a great question. Yeah, great question. Let's do some examples here. Okay. So we're going to find residues. Ooh, what's this? This is oh shit! Here's one really easy. One more result. I forgot to show you this one. This is a great one. Good theorem. If you have a simple pole, if F has a simple pole at Z equals Z naught, then the residue and F of Z is a quotient. So what does that mean? So in your head, what does this mean? A simple pole Z equals Z naught. What does that mean about G and H at Z naught?
G of Z naught doesn't equal 0.
And H does, but it's.
And H does, right? So the bottom's going to 0 with a 0 of multiplicity 1, and the top is non-zero. So let's just make a little note here. So G of Z naught is not 0, but H of Z equals 0. And what about H prime of Z naught? So this equals 0.
Not 0.
Not 0. Yeah. Because this has a 0 multiplicity 1. And that means when you plug in the thing, you get 0, but then from an arrow on out, derivatives are non-zero. All right, so if this is the case, watch this cool little trick. And I'm gonna drive us and derive us there. So this is equal to Z minus Z naught times G of Z over hold on. yeah, okay, so then we've got this. So to get the simple pole, to get the residue, so the residue of f at z naught will equal limit as z goes to z naught of this quotient times this dude here. So this was the very first residue formula I gave you, and I'm just plugging in this for that. But here's the game. This is actually, we're gonna do a slick maneuver.
Ooh.
Slick.
Ew, COVID.
And we need one other fact. We have to remember that h at z naught is 0. So I'm gonna rewrite this. Since h at z naught equals 0, this is just, rewrite it again, limit as z goes to z naught of g of z over, now watch, I'm gonna put h of z minus h of z naught over z minus z naught. And I can do that because that's just 0. And then I'm gonna bring, what happens if you bring the limit underneath? What do you get in the bottom? What is the limit as z goes to z naught of this quantity?
Approaching 0.
It is approaching 0 over 0. This is a good calc
It's a
quantity.
derivative.
It's the derivative at z naught. Exactly. So this is g at z naught over h prime at z naught. Man, is this useful. If you have a simple pole in a fraction, take the derivative of the bottom, leave the top alone, and plug the point of trouble in. So let's now do some of these.
Another quick question.
Yes, sir. Yeah.
Why do we care?
What's that?
Why do we care about the residue?
Read the residue theorem.
Was that a thing I missed?
What's that?
Was that a thing I missed or reading for next week?
That was probably something you did miss when I didn't post the recording. But I didn't cover it, but I did recommend reading it.
Okay.
So what we're gonna do is we're gonna turn every integral into just needing the residues.
Oh,
Yeah.
that's useful.
It's very cool. It's so powerful and beautiful. And then once we do that, then we can do all sorts of crazy real integrals that are impossible without calc or without complex analysis and the residue theorem. But do read that note. I think you'll see the great power of it. So example time. All right, find the residue of, and this looks like a 2 over z minus 1, z minus 4 at z equals 1. So let's look and let's first understand that we're dividing by 0, so we have some kind of a pole. We have to figure out the depth of the pole. So notice that this function can be written like this. The top thing is not 0 at z equals 1, but the bottom is. So it's just like what I've got over there. It's exactly like this thing that I just had. That's the g of z, that's the h of z. What is the residue? All I'm saying here is that to find that residue, I take the derivative of the denominator, the part that's making this thing non-analytic. So notice I left the z minus 1 in the bottom, pulled the z minus 4 on top, this is kosher at 1, this is not, using that result. And using our definition, this is a pole, this is a simple pole. So a pole of order 1 there. And to find that residue, I just leave the top alone, plug in 1, take the derivative of the bottom, plug in 1. Well, the derivative of the bottom is 1, so what's my residue here?
Negative 2/3.
Negative 2/3. Let's do another. Give you one. Okay, so. Yeah, that wasn't the original problem I had. Oh well. So here we've got 4z minus 6, let's call this f. 4z minus 6 over 2z minus z squared. Please find the residue at 0. I'm gonna run to the restroom. You can do exactly what we just did, just practice doing that. Might need to factor a little. You do want to factor that denominator. That. Pull the 0 part into the bottom, pull the 2 minus z part on top. Doesn't get much easier than differentiating z, besides not doing differentiation at all. So take the derivative, so the residue of f at 0 equals 4 times 0 minus 6 over 2 minus 0, which is 2, over the derivative of the bottom at 0, which is just 1, and our residue is negative 3. Maybe I'll just leave. I would recommend to you to practice this over the break. So my recommendation is to read section 6.5, but go through some of these exercise 6.5 on page 300, do the odds, find those residues and check yourself. And shoot me an email if you have any troubles. I also put up some extra problems for you to do, for those who just don't have enough to do. There's problems up, they're optional.
Who could you be referring to?
I wonder, so, Lou's been asking for more, you might want more. Anyone who wants more, there's some fun problems up there. You want bonus, sure, I'll give you bonus problem. You can have bonus points for them. Do the damn work first that's required. I cussed. Is that a cuss?
I don't think so.
I don't think so.
They said ass on Jeopardy recently, and I was shocked.
What is that?
They said ass on Jeopardy, and I was like, you can say
Were they
that on
talking about
Jeopardy?
donkeys?
No, they were talking. It was
Like is the
uh,
gluteus maximus?
yeah.
Wow.
And so I guess that's